Okay, so let's see one numerical on PCA, principal component analysis. So we have already seen and studied about the PCA, principal component analysis. That this is a dimensionality reduction technique. Okay, so let's see an example how to solve or how to find the first principal component for a data set. Okay, so let's consider this data set. Okay, so let's consider these two features. Let's x and y. Okay, so these are the features. These are the features, and this is sample x1, x2, x3, x4. These are the four samples. Okay, so number of samples are four, and number of features are two. Okay, and we want to find the first principal component for this data set. Okay, first principal component means we want to, so currently these data points are in 2D, two dimensions. So now we want to uh, create a new data set which is in 1D, one dimension. Okay, so for that the first thing is we want to find the mean. We want to find we need to find the mean for each feature. So we basically find the x bar and y bar. So x bar would be 4 plus 8 plus 13 plus 7 by 4. So we add all these four terms and divide it by 4. So how much it would be? So 32 by 4 is 8. And this would be 11 plus 4 plus 5 plus 14 divided by 4. This would come as 15, 20, 34 by 4. So this would come as 8 point. Okay. So this is our mean, x bar and y bar. Now, second step is find the covariance matrix. Covariance matrix, so we have already seen what is the covariance matrix, sigma. We represent this covariance matrix by sigma. Okay, so this covariance matrix of uh, so covariance matrix is like x comma x, x comma y comma x, and y. Okay, for let's say x comma y. So the formula is, so 1 by number of samples minus 1. So this is n, and let's say this is m. Okay, so 1 by n minus 1 summation I is equal to 1 to n xi minus x bar into yi minus y bar. Okay, and uh, so let's first find out this. Okay, so covariance of x comma y. So this covariance of x comma y, it would be 1 by 4 minus 1. Now our first data sample is 4 and 11. So 4 minus x bar is 8. 4 minus 8 into yi is 11 minus 8 plus 8 minus 8 into 4 minus 8.5 plus 13 minus 8 into 5 minus 8.5 plus 7 minus 8 into 14 minus 8.5. Okay, you solve it, so you'll get it minus 11. Okay, so now if covariance of x comma y is minus 11, so covariance of y comma x would also be minus 11, because here you can see just this bracket gets swapped. Okay, so the product remains same, so both these values are symmetric, so this remains same. Now covariance of x comma x, that would be 1 minus 1 by n minus 1 summation of I equal to 1 to n xi minus x bar into xi minus x bar. Okay, so basically it would be 1 minus by n minus 1 summation over I equal to 1 to n. You can write it as xi minus x bar square. So 1 by 4 minus 1 summation. So we can write it as 4 minus 8 square plus, so let's see the data, 8 minus 8 square plus 13 minus 8 square plus 7 minus 8 square. Okay, so if you solve this, you will get 40. So covariance of x comma x is 40. And similarly, you can get covariance of y comma y is equal to 1 by n minus 1 summation over I equal to 1 to n yi minus y bar square. Okay, it would be 1 by 4 minus 1, so 1 by 4 minus 1 into 11 minus 8.5 square plus 4 minus 8.5 square plus 5 minus 8.5 square plus 14 minus 8.5 square. Okay, so if you solve this, we'll get 23. Okay, so what is the final covariance matrix? The covariance matrix return as 14 minus 11 and 23. Okay, so now the third step is we find the eigenvalues. Okay, so find the eigenvalues. What is the formula values is S minus lambda I determinant is equal to 0. So this is the covariance matrix represented by S. Okay, so S is the covariance matrix, lambda is the eigenvalue, and I is the identity matrix. Okay, so this covariance matrix is 2 by 2. So the corresponding identity matrix would also be uh, uh, 2 by 2. Okay, so if you solve this, so this would come as 14 minus 11 23 minus lambda into 1 0 0 1, and the determinant of that is equal to 0. You can see here 14 minus lambda minus 11 minus 11 and 23 minus lambda determinant equal to 0. You can see here 14 minus lambda, 23 minus lambda, and minus 121 equals 0. Okay, just solve this. That's what you will get. Okay, so after that, this would result in a quadratic equation. In a quadratic equation in lambda, this would result in a quadratic equation in lambda. Solve and the values you will get would be equals to 30.3849 and lambda 2 would be 6.615. Okay, so these are the two eigenvalues. So remember that the larger eigenvalue would be the first principal component. Okay, so here lambda 1 is greater than lambda 2. Okay, so now we find the fourth step is find the eigenvector. So we find the corresponding eigenvector. We find the eigenvector. For the eigenvector, so what is the expression? So we find the eigenvector for corresponding to lambda, because lambda 1 is greater than lambda 2. So lambda 1 would be the would give us the first principal component. Okay, so here, so lambda 1 I into u1. U1 is is the eigenvector, the corresponding eigenvector, and that's this is 0. Okay, so this we can take from here. So this is 14 minus lambda minus 11 minus 11, 23 minus lambda. So this is lambda 1. Okay, and this is 2 cross 1 matrix u1, small u1 and u2, and this is 0. Okay, so when you solve this equation, so this would give you 14 minus lambda 1 u1 minus 11 u2 minus 11 u1 plus 23 minus lambda 1 u2. Okay, so there would be two equations. So 14 minus lambda 1 u1 minus 11 u2 equals to 0, and minus 11 u1 plus 23 minus lambda 1 u2 equals to 0. Using these two equations, okay, so you can put the lambda 1 values and you can solve for u1 and u2. Okay, so the u1 vector would return as 11 and minus 16.3849. Okay, so this is not normalized. Okay, so the normalized, so normalized u1 would be, how we calculate the normalized eigenvector, 11 by under root 11 square plus minus 16.3849 square and minus 16.3849 divided by 11 square plus minus 16.3849. Okay, so this would give you 0.5574 minus 0.8303. And in the similar fashion, you can get the normalized U2 vector. Okay, so let me write it. So U1 is 0.5574 minus 0.8303, and U2 is 0.8303 and 0.557. Okay, so this is the first component. So this is the final answer, that first principal component is this eigenvector u1, okay, and the first eigenvalue is lambda 1 30.3849. Okay, and also you can now represent uh, your original data into 1D using this first principal component. Okay, so let me just show you how. So let's just copy that data. Okay, and let's just copy this part. Okay, so now we have data with ourselves. Okay, okay, so we have the data set with the original data set. So this was the original or given data set. This was the mean. This was the mean. Okay, and this was the first principal component that. Okay. Now, how we can construct the new data set? The new data set would be of this form. So, okay, so this is first principal component P1, and there would be this P11, P12, P13, and P1. Okay, okay. So now how we calculate is, let's see. So P11, the uh, first sample, how it can be calculated is, we take the first eigenvector, or this eigenvector corresponding, and xi minus x bar, and the corresponding yi minus. So basically this transpose, so this would be 0.5574 minus 0.8303, and this would be, so x is 4, so 4 minus mean is 8, so 4 minus 8, and 11 minus 8, 11 minus, okay, so this would result in minus 4.30. So here it would get minus 4.3052. Similarly, you'll get P12 as 3.7361, P13 is 5.6928, and the P14 is minus 5.123. Okay, so these are the 1D representations of the given data samples, given 2D samples. Okay, and if you plot this on the graph, then also you'll get the uh, uh, same representations of the original data samples using this. Okay, okay, sir. Let's stop here.